That's 12 noon, folks. So I'm going to go ahead and welcome us all. Hi, I'm Jeff Jensen, Program Manager, Field Coordinator with Trees Forever. Welcome to this fascinating webinar that we have here today. Just a couple of housekeeping items before I turn it over to Phil.
All right. Well, my name is Phil Kerr. I work for the Iowa Geological Survey. I live in Iowa City. I grew up between LeGrand and Gilman in Marshall County. So I'm studying an area that's pretty close to home. And what I do for a living is I'm a quaternary geologist. So that means I study the last 2.56 million years in Iowa. And that is really lucky for me because Iowa is probably the most complete record of glaciation on land in North America. And so part of that is understanding how the rest of the system interacts with that. And one of the things that have been fascinating geologists and bewitching them for a while is pajas. There are these lineated hills in eastern Iowa. And I've been working in this area, and I'll kind of talk to you about that. But overall, this is a reevaluation of the Iowan surface, which is a landform region in Iowa. And if you saw my previous presentation with Trees Forever, you might be familiar with that. So I'm going to shut off my camera so you can really bask in this slideshow, and we'll get through it. All right, turn that off. So once again, as Jeff pointed out, if you have any questions, please type them into the chat box. Oh, it looks like, yeah, Jim's got that one. Okay, so this is what we're looking at. This is Iowa, and Iowa is between the Missouri and the Mississippi. It's pretty, just a phenomenally wild state, and it's broken up into landforms. And these landforms are a rough breakdown between how the landscape looks. And you can see here it's a little off center, but whatever, it's fine. And we'll be looking at the Iowan surface, which is in eastern and northeastern Iowa. So the real story, though, is what's going on with the rest of North America. And it's a pretty interesting tale about how this fits into it. And so you can see just how much glaciers have shaped this area. They slide in from the north and into Iowa, and from the east through the Great Lakes into states adjacent to us. And this Iowan surface, or it's more commonly called the Iowan erosion surface out of state, well, it's a 100-year debate, and it's a debate between glacial and non-glacial influence and processes. The mechanisms aren't really, or haven't been really understood, and the shape of it is pretty interesting too. So it's this area in here, into a little more detail about it. Some of you might be familiar, some of you might even live here, but it's an area of gently rolling terrain, so not steep. It doesn't have a lot of steep slopes. If you want to get really steep, you have to go a little bit further to the northeast into the Paleozoic plateau, and it has glacial sediments in it. And those glacial sediments can be thin or thick, and they sit over generally Devonian carbonate, and that carbonate can outcrop in certain areas. And the most fascinating part that's been, again, bewitching people for a long time is these paha, and I'll talk about those more. So this is where it is in Iowa, and you can see this tan color is loess, and the loess, well, there's a lack of loess in it. And where is it? So this is a figure of all of the Midwest and the loess. So loess is Aeolian deposited silt. Some of you might call it clay or yellow clay, depending on where you are. But what it is, it's material that's blown in from river valleys onto the landscape, and it provides a lot of Iowa with its topsoil. But the problem with the Iowan surface is there's no loess in it, and the boundary of it is pretty bizarre. It looks like someone threw an octopus or a squid on it and traced it. So you can see here there's a zone of thick loess around it, and that has been confusing people since the 1800s. So the previous interpretations are an ice advance or fluvial erosion, cutting down by streams, an ice burst flood, some people even think, or snow dune melting. And I'll tell you why they're kind of wrong here, hopefully. So this is the key idea. I want to plant this seed in your head so you kind of look for something as you go along. And the key idea is to look at the landscape in a certain orientation and compare it to other landscapes in Iowa. In this case, we're going to be comparing it to the southern Iowa drift plain, so the area basically south of the Iowa River. And we'll be looking at it in a west-northwest orientation, and we'll be trying to understand if the landscape is flat in front of a certain spot or if there's a steep wall. So one of the things that I want to get across to you too is if you look at the landscape, if you look at the shape of erosion, the shape of geomorphology, it'll tell you a little bit about what's going on. So the difference between the Appalachian Mountains and the Rocky Mountains is great, but there's still two mountain ranges formed by relatively the same process. It's just that time has played on them for millions and millions of years longer in the Appalachians, basically wearing them down to the root. The Colorado River or the Colorado Rockies the Rockies are pretty new and fresh. The same thing is going on between western Nebraska and South Dakota, where western Nebraska is pretty flat and has these rivers that go east to west, but South Dakota has a completely different shape. And so this is the difference between fluvial erosion and glacial topography. And the scales of these things change dramatically. In Iowa, we have a lot of these same features too, except for save for the mountains, of course. But the strongest influence on the landscape is glacial topography and glacial advance and retreat, and that gives the general shape of the landscape. Then we have fluvial erosion, as you can see in this box here. And we also have Aeolian deposition as well. And all of these are affected by time. So geology is the study of materials and time, and you can look at the material and think about how that changes over time. So let's talk about time. What's going on in Iowa? Well, Iowa has been glaciated multiple times, and that has really affected how the topography is going to behave. So the most recent one, the Des Moines lobe, is in the very center of the state, and there was a more recent advance east of that at 30,000 years ago. And then there was another one potentially over here. We'll talk more about that. And then Illinoisan advance from the east, which disturbed a lot of rivers. And then the rest of Iowa was glaciated multiple times over the last 500,000 or between 0.5 million years ago and 2.5 million years ago. So I would say that the time of glaciation is one of the biggest factors on how the landscape looks. And to talk about materials now, as a geologist, I use something called stratigraphy. So if you think about how a cake is formed, you have the base layer, you put some frosting on, you have another layer, then you put some frosting on, and you can stack that. And each layer and frosting would be a different stratigraphic unit. And so in Iowa, the tills, the glacial sediments, are the layers of cake, and then we have paleosols and loess, windblown silt, that form in between them. And the most recent advances are clearly the freshest because they haven't had much time to change. So what I've done to study this area, to look at it, I've mapped it, I've taken cores, I've drilled it with other methods, and I've also done geographical information system analysis, or GIS analysis. And so over the last year, I've been a little cooped up at home, so I mapped over 4,000 features dealing with this part of Iowa. And as part of that, you can really start to understand what's going on if you look at it in a systematic way. And I'll describe that later on. And so with radiocarbon aging or dating, what that does is it tells you when or when not an advance of ice happened, because it runs over trees, and if you find a tree, you can date it using radiocarbon techniques. And so what I've been mapping over the last year, though, are dunes. Iowa actually has a lot of sand dunes. If you've heard about the painted box turtle, you can find them in these sandy areas. So this is applicable to ecological studies. And the other features I've been studying are these kind of bizarre linear features, where you just have these oriented grooves or patterns on the landscape. And if you map all of them out, you can see a trend. So you can see that they look like they're two very different things, where you have this steep hill here and these gentle troughs. So I should illustrate, or I should comment on these colors here. I use slope maps, and the slope here, the steeper the slope, the darker the blue. So flat areas are more greenish white, and the steeper areas are dark blue. So before we get really going, we should just briefly talk about materials, just so everyone's on the same page. When I say loess, what I'm talking about is particles that were suspended in the wind, so up in the air, similar or what you would call dust. When I say till, that's sediment that's laid down under a glacier and is clay rich, it's pretty hard, and it takes a lot of energy to move it. And when I talk about a paleosol, what that is an old soil that was buried either by till or by loss. And these soils reflect a time when there was soil formation going on that was then subsequently buried by some geologic process. The other thing that these materials do is they have different properties, and that's why slope is such an important thing, because each different material has a different yield stress. And so if you stack, for instance, a pile of sand versus a pile of playing cards, you can get the playing cards much higher than the pile of sand. Well, the same thing is true with till and loess. They have a certain characteristic in how they interact with water and gravity and themselves. So basically, you can look at materials and say, well, if this steep hill is formed in a certain way, it's probably capped by loess. Or if it's really flat, it's not, and there's no loess, it's all till. Because you can stack loess steep. Look at the loess hills and how they're cut in western Iowa. It's a great example. And here's an example of that. This is till, and these little blips are sand dunes, so they have a different slope. But these steep slopes right here, this is loess. And so there's some kind of boundary here, and that's what I'm looking at. All right, so back to the Iowan erosion surface. It's interesting because, hey, guess what? It's almost 1% of the United States. So it's probably important that we figure out almost 1/100th of our nation here geologically. And as we said before, it's flatter, but it has an integrated drainage network, and that's important because that means it isn't new like the Des Moines lobe is. And we've been over the loess cover, and it doesn't have paleosols under that loess like the southern Iowa drift plain. And there's relatively no paleosols at the surface either. And this is what it looks like in the northern part. This is outside of Charles City in Floyd County, and this is one of the counties I mapped. And this is in Chickasaw County, and here you can see one of the diagnostic features of the Iowan surface. You find these erratics at the surface. And so this is what people have said over the last 100 years is pretty characteristic of this area, where you have boulders moved down from Canada or Minnesota left at the surface. Well, they're left at the surface for different processes, and they're exposed for different reasons, and hopefully I can talk to you about that. So Iowa, the Iowan surface is a palimpsest. And what I mean by that is there's areas that look like they're old that have had the rest of the area erased around it. So palimpsest, the lambskin, I think it's a Latin word, where you would write and then erase if you want to write something new. And then when we write again, you can see little bits of the old writing through that. And this area is pretty wild because these paha, these black lines here, are thought to be these relic features, these older landscapes, but they're not really. So another aspect of this Iowan palimpsest is the bedrock itself. And so the bedrock doesn't reflect the modern topography because we've had so many glacial advances. And each time a glacier would advance, it would bury old valleys. And so now we have areas where there can be over 300 feet of glacial till before you hit bedrock. And that's a key feature in this region. And I should point out that the surface water isn't controlled by bedrock like it is in most other areas. So you'd expect rivers to behave and follow trends between different lithologies. So you'd have a river behaving differently in shale versus carbonate. But since there's no bedrock exposed in some of these areas, the rivers don't strictly behave due to that. So here's an example of the field stuff that I do. I go out and look at cores down here and outcrops. So here's loess in a core, but here's loess and sand in an outcrop. And this is for a USGS project called State Map. So I actually go out and make geologic maps for a living. And in doing so, I can find these patterns and really explore them. So what are the insights that I'm hoping to find here? Well, one of the things that I'm hoping to look at is processes. So how do things form? Geomorphology. I'm also trying to explain the paha and their connection to the loess and glaciers. And then all of these related to Aeolian sand, because one of the things that all of these signal is that there is a different climate when these changes were occurring. So the process that formed the Iowan erosion surface isn't ongoing. All right, so we should talk real quick about the history of study. The first people to notice paha and these patterns are Native Americans. And here's a pretty grainy picture, but you can see your burial mounds on top of thick loess right adjacent to the Cedar River. And so these people were informed about the high spots in the area. Good for them, because that's where you can see all the changes. One of the first European descended people to look at this area was McGee, and he noticed these paha here and described them. You can see this beautiful lithograph print. He described them as the elongated swell of soft and graceful contours, standing apart on the plain, or else connected with its fellows sometimes in long lines, again in congeries, and locally merging to form broad plateaus. You know, I like that flowery prose, but the thing is, that's not exactly how those paha look. They don't form congeries or groups, and they don't merge because they're not like a pod of whales. It's just, you know, inaccurate, but it sounds really nice. So here's the stratigraphy of a paha. You have this area where the paleosol is supposed to be preserved. So this reflects an old surface. The Sangamon soil was forming from 130,000 years ago to maybe 30,000 years ago. It's formed in this glacial till, and it's buried by this Aeolian dust, this loess. And so that is what a paha is supposed to be. And one of the early explanations for this was, for this area in paha, was that it's part of a glacial stage called the Iowan. And that was supposed to be before the last advance, the Wisconsin, and between the Illinoisan. And so this lack of loess was indicative of older researchers, and they said, well, this shape, since it has no loess, it has to be fresh. But the problem is it doesn't really work because, once again, the shape of it is so much different than an ice lobe. So how do you get ice moving in these small tongues? Well, how do you explain paha? Well, what they did was they said, well, these paha, since they have that old soil, well, they were preserved, and the material around them was eroded by ice. So you have this older till sticking out from this younger ice advance. It's just kind of bizarre. So this is kind of an illustration of how they thought about it. So these are a line of paha in Benton County near Highway 30. They thought the ice kind of flowed around them in little tongues. And glaciologically, it doesn't work, because how are you going to have a continental ice sheet avoid certain areas like this? It just doesn't make sense. So this is where we have to get into more modern work, and this is part 2, Je ne sais paha. And we are now introduced to Robert Victory Ruy, one of the more famous geomorphologists and pedologists in the 20th century in the Midwest, mid-20th century, I should say. And he looked at the Iowan drift problem and said, well, you know what, this shape, the drift, it doesn't make sense. You're not going to have this glacial or glacier advance like that. And what he did was he conducted a coring campaign and showed that this till, the Iowan till, is actually the same as the Kansan till. It just had the Sangamon removed. So it's like you take a car and you just buff some of the rust off, and now you have a shiny metal surface. Well, that doesn't make it newer than the same, or the door on the same car that still has the rust. They're the same age, it just looks newer. How he explained that was pedimentation, and that's the slow cutting of a landscape due to fluvial incision. And so this is an example of how that goes over time. So you have a fresh surface like a glacial advance, and then rivers cut down into that over time. This is how he illustrated it. So you have the interfluve, the area between two drainages, as the highest spot, you know, the watershed divide. And then you have a period of loess deposition. Now, Ruy never said where the loess came from or when it came, he just said it came for some reason, not from where either. And then you had a period when the rivers cut down, and that changed the landscape. And so you have back cutting due to deeper rivers, and that would affect the landscape, removing the Sangamon in his model, but it would stop at some point. And then the rest of the landscape would continue eroding, but preserving the interfluves, removing the Sangamon, and then eventually you get a paha between these rivers. And that's one of the things about this geomorphology and the shape of it. If you have something that's dominated by a fluvial process, it has to follow water moving across the landscape. Or what I'm saying is it has to be within a watershed. And that's one of the problems. So eventually, though, he said, there's no Iowan, it's gone. But his interpretation, I think, is off. Because if we look at the interfluve, you know, the area between streams, which one is it? Shouldn't the paha be here too? Wait, why is it between these really small first order streams? And again, there's no stream over here, so why is there this paha here? And this is in Benton County where I've been mapping. So I've cored this. I've looked at this area pretty thoroughly. And why isn't there pahas on this side? Well, it's even more confusing is further to the east. This is the Cedar River drainage over here, and this is the Wapsipinicon, two big rivers. But the paha cut across the watershed. So these can't have been formed by moving water. If it cuts across watersheds, it doesn't make sense. The erosion has to line up with the process. And so you have to have a process that cuts across watersheds. Well, there's a couple that can do that. And another problem is, well, some of these paha don't have a well-preserved Sangamon geosol. It's missing in some places. So what that means is there was a period when there was erosion on the entire surface, not just the areas that Rui said. So it just disproves his fluvial interpretation. And these big inliers that McGee called congeries, well, they're not relics either. They don't reflect an old landscape, and they don't often have paleosols either. All right, so now we're going to get into the fantasy and mysticism section, which is where I come in and interpret things based on my experiences. So one of the things that you have to start thinking about is all of North America, because the glacial history of Iowa is tied to the rest of the continent. And one thing that is really neat is that, well, there's pre-Illinoisan advances, and we can see them on the surface if we look at them with a certain interpretation. So the last pre-Illinoisan advance probably followed the same pathway as the Des Moines lobe, but kept going into eastern Iowa. And why do I think that? Well, let me show it to you. So the glacial effect on the landscape, if we use, you know, the rule of uniformitarianism, the processes that is happening today probably happened in the past as well. Well, the most recent advance, the Des Moines lobe, you can see the relationship between moraines, hills left by glacial retreat and advance, and the landscape that developed after the ice retreated. So the orange lines here are moraines, and the black are streams. And you can see that the streams are perpendicular or parallel to these moraines, which makes sense because of the high spots in the landscape. And you have this giant block of melting ice, it's really going to set up how the landscape and drainage network is. And I made a little model to illustrate that. So one of the key things to look at is this relationship right here, this river. So imagine this is the Des Moines lobe. This would be the Cedar, the Iowa, and the Des Moines. And as ice comes down and reaches Des Moines, you form a moraine. This is the Bemis moraine. The capital sits about right here. And then you form a new river here. This is the Raccoon, the Southern Raccoon. And then as the ice retreats, as it melts back, you form this radial pattern of drainages that point towards the ice front, which is a lobe, and that's why you have this radial pattern. Ice can also advance and retreat quickly, and these form a lot of small moraines. And when that happens, these moraines form small drainages that are between them, they're parallel. And so you have this Des Moines River coming up and draining along the axis of this lobe shape. An axial river is what I'm calling it. And over time, then that's your river system. And there's so much water that the modern drainage can't disrupt that. And that's why we see these patterns. So streams are either perpendicular or parallel to moraines. But over time, these moraines, these high spots, get eroded out, but the channels, the orientation of them, aren't going to drastically change because there's no process in Iowa, like tectonic uplift or volcanic eruption, that can override these. Ice is the major player in this area. And that's why we can use the Des Moines lobe and kind of use it as a model. So we can take it, rotate it a bit, not that much, but we can rotate it and look at that. It fits right over the Iowa River, Prairie Creek, and the Cedar. So you can see the same pattern where you have this curving of the Iowa River and the Raccoon, and the axial drainage of the Cedar and the Des Moines. And you also have Prairie Creek coming on the other side of the moraine, similar to these streams here. So the Iowan surface, well, it actually is a glacial boundary, but not quite, because the ice sheet doesn't really match the boundary that's formed by the Iowan surface. And so here's a more zoomed in version. You can see this is the Iowa River. And it can't, this pattern can't be due to bedrock because there's no bedrock from here. There's one little outcrop here, and it's mined by Wendling quarries, to here. It's all deep till. So something had to put in place, and it can't be controlled by bedrock. And if we look at the line here, you can see there's a great pattern that cuts across these watersheds that is probably the remnant of an ice advance. Because once again, you can't have fluvial patterns cutting across, or you can't have patterns cutting across watersheds caused by fluvial erosion. It has to be something else. And there was a more recent glaciation during the Wisconsin that I spent my master's degree was sussing out, and that is in north central Iowa. So that's up in here, and you can see how it affects the watersheds too. So in northeast or northwestern Iowa, it really changes how these drainages come into play. So instead of having dendritic, where you have more acute angles, these streams come in at right angles. So very similar to how the Cedar, or how streams in the Cedar River come into them as well. All right, so now we're going to get to part 3, the climate toolbox, or why is the Iowan erosion surface so flat? So this is more recent. This is during the last glacial period. So during the Wisconsin, it was much colder, and we know that because there was a lot of studies done showing that insects and trees during that time were from northern Canada. So the same species exists there, so it had to be much colder, nearly 20 degrees colder in the summertime than it is now. Which actually, that sounds pretty nice today in this week. So this boundary, this glacial boundary, isn't correct because this represents the maximum advance. But the Des Moines lobe actually came in much later. So the real glacial boundary during most of the Wisconsin would have been something like this. Now what that does is it affects the jet stream and the core and the westerlies. So the wind in Iowa would have been coming pretty steadily from the northwest. So this Wisconsin shift, this is the modern climate. And if we shift it down 20 degrees, well, guess what? Now you have more time when it's below 0. So what that does, well, this is freezing, so 0 degrees centigrade. So below freezing, what that does is it creates permafrost. So you're not going to be able to thaw the ground all the time. So you're going to get ice in the soil. So imagine if you go out in the dead of winter, there's going to be frost in the soil, but in this time period, it never went away. And what that sets up is a system where there's an active layer that thaws each year due to solar radiation heating it up, but then the ground underneath it is still going to be frozen. So that is a pretty wild thing, and we see the consequences of that in Canada and Russia today. And the thing to keep in mind is these processes that happen, they are not just slow creeps. They're not just little changes, they're drastic. One of them, or most of the changes that occur that are really drastic occur at the end, and they're due to thermokarsting. What that is you have melting of the permafrost, and that adds water to the system, which then decreases the strength of the active layer, basically turning it into a slurry. And so there's two main things that I want to talk about quickly: active layer detachments and regressive thaw slumps. So active layer detachments occur when you have established slopes. And this is when you have an active layer that is above your permafrost, and something happens, like it rains, or there's some of the melting of the permafrost, and that creates a slide plane. You know, basically this active layer up here is or is floated and then slides down off of this permafrost. And keep in mind, this isn't entirely ice, it's just material with water in the pores, so it's like concrete. It's really hard and it's impenetrable to water. And so over time, you form a new active layer over the next couple melt seasons or later in the year. And then if something happens to disturb that again, you'll have another mass flow. And the result of that is you completely bevel off the landscape. So you take what was once high and you put that in the low spots. So you balance things out. And this is what it looks like in practice. So this is in Alaska, and you can see some of these things are wildly large. These little dots right here are people. So this is huge. This is thousands of cubic yards of material moving at once, downslope because of gravity. And this is a process that doesn't erase the landscape, it just mutes it. And so this is why part of the erosion surface is the way it is. So the other thing that is important in some parts is regressive thaw slumps. So if you have a river, let's say, that's carrying meltwater from a melting glacier, you're going to have a talus or an unfrozen part of the landscape that's going to be thawed, and the rest of the landscape is still going to be frozen. Well, over time, what could happen is you form gullies due to the water thawing the landscape, but it's not going to thaw it as a huge front. It's going to kind of find crevices and weaknesses. And then those are going to thaw, and they're going to cut back. And what happens when you really heat up the landscape is the permafrost is going to thaw there. But what that does is it creates instabilities, and you're going to have these regressive thaw slumps. And so they look like basins because you're just basically melting the landscape and then pumping all of that into rivers as a mud slurry. And this is very common up in north central Iowa, like in Floyd and Mitchell counties. And this confused me when I was mapping, because how do you form almost half a mile wide basins like this in glacial sediment? Well, it makes sense if it was frozen and then thawed rapidly. So you can see a line here where that occurred in this small creek. And Osage is really the poster child for this, because you can see all of these regressive thaw slumps completely cutting into the landscape. And so this contributes to the unique topography up there and why you don't have a lot of streams cutting in, because it's a newer surface, because it's more recently glaciated, and also the process is completely bizarre and doesn't allow for the formation of integrated drainage networks rapidly. And this is what it looks like. So imagine trying to move this with modern drainage today. So this would just be vegetated and people would farm it. This is one of the best examples from Russia. So you can see how this is permafrosted, the area with the green, and then it just completely melts the landscape, and then you expose so much sediment for erosion. And there's two major regions for regressive thaw slumps, what we just talked about, and the active layer detachments. So the area that was recently glaciated up here in north central Iowa is much flatter and has these weird basins in it, or regressive thaw slumps. And the rest of the Iowan erosion surface has active layer detachments, and that's why there's no Sangamon. That's why this material has been removed, because this clay-rich sediment is really going to hold on to water, and when it melts, it's just going to wash away. And we can use the Iowan, or we can look at the Iowan surface as a reflection from the Des Moines lobe and the southern Iowa drift plain and say, hey, this initial drainage pattern, well, if you freeze it, this is what it's going to look like. You're going to take these deeply incised channels and then just slump them out. You're going to create these big basins. And if you take southern Iowa, which has topography formed, and then put that in the freezer, you're going to level it all out and bevel down your hills and fill in your valleys. And you can see how much wider these streams are than in southern Iowa. Well, that's because they're filled with sand and gravel. And I know that because I've drilled them. So it's no coincidence that these two areas are different because they've been more recently glaciated in the more northern parts. So that's why part of this is flatter. So let's talk about the wind again. And there's numerous indicators on the landscape across multiple states that the wind is from the northwest. So this is when you have the jet stream probably locking on to this ice front, and it's just going to bombard the landscape with really strong winds. And this isn't coming off the ice sheet because that only extends a couple, maybe 50 to 70 miles off. And we're much farther from the ice sheet than areas up here in Wisconsin or Minnesota or parts of Illinois during this time, because ice came into Iowa rapidly and retreated quickly. So in less than 2,000 years, ice was to its furthest extent in Des Moines and then out of the state again. And hey, models actually agree with that now. So this is more academic, but you know, it's good to have these people agree with you. So this leads us to part 3.2, which is Je ne sais pas how to at a lust for words. I'm really sorry about that. Like, yeah, that transition's a bit much. So what is going on here? There is so much Aeolian sand on this landscape that it fills in giant cracks in the landscape. So this is all windblown sand wedged into till at the top of a hill outside of Garrison, Iowa, in Benton County. And there's I think 5 yards of it here, so 15 feet deep. And so you have these sands filling in because the ground is freezing and cracking, and then you pump sand in, and then it holds it open, and then it freezes again, and then you continue this pattern again and again, filling it with sand. So it was cold and windy, and because it was so cold, there's little vegetation, so sand can really blow across it. And that sand is coming from outwash. As you have ice in the area, you're putting in meltwater. So there's outwash from both advances of the ice sheet, the recent and older ones, and those fill the Iowa and the Cedar rivers, which are the 2 main rivers in the area, but not the Wapsipinicon. So I'll talk about that in a bit. So when you have this outwash, what it does is it loads the rivers with material, coarse sand, boulders, gravel, silt, clay, all of it. And then since it's from a melting glacier, you get a lot of meltwater in the late spring, summer, and then towards the fall, it shuts off. So then you just have all this material laying out for the wind to pick up during the winter and spring seasons. And that leads to this area being a transport surface. So it's flat due to this active layer detachment. It's flat due to it being more recently glaciated, so it doesn't have as much time to form topography. And so that just allows the sand, once it is going to blow across. So this is where all of this sand is located that I'm showing you. And there's a whole lot of sand. Look at that. So that is a ventifact. That's a piece of Sioux quartzite, and it has these pits from being blasted by sand. It's pretty wild. It's my favorite hand sample I've come across. So these sand wedges indicate that it's cold and dry, which, oh, here's a person for scale. This is my intern Dan, and he's really stoked about them. And once again, it's flat from recent glaciations and periglacial tomfoolery, leading it to be a trend. Oh, I duplicated slides. So anyway, outwash is the source of sand, and that allows it to move across the landscape, but it's controlled by the shape and form of the valleys. So the valleys have to allow sand to get out. And that's what this transport surface is key, because once sand gets out, what it can do is erode. Because sand doesn't get up into the landscape, it bounces, it saltates. Or another way to put it, it sandblasts the landscape. So these outwash filled rivers are pumping out sand, and depending on where the sand can and can't get out is where you're going to have material be sandblasted or not. And if we think about this dust, it's going to be easily sandblasted, because as the sand goes along, it's going to transfer that energy into the landscape, blowing that, or hitting that lust, and then it's going to get into the air, which is moving the sand as well. And we see evidence of that, and once again, in this vent effect. So this is the topographic control. This is why it matters what's upwind of something. Because if you have a flat surface, like most of the Iowan erosion surface, you're just going to have the sand move across and deflate. So deflate is another word for sandblasting. So if you have lust coming in, it tries to settle down, but then sand during the same storm or a later storm, later in the year or years later, there's not much vegetation to hold it, it's going to get blasted. But if you have an area where sand can't go, like a stream valley that has a bedrock wall, well, that's where you're going to get your lust deposit. The same thing works if you have a deeply incised stream. Wind can't come in and scoop that out, so sand just falls in, and then you get a lust deposit downwind. Joe Mason came up with this model based on work in Nebraska and southern Minnesota. And this is why Iowa is unique, because we have this relationship of glacial advance, bedrock channels, glacial advance forming different bedrock channels. And so where you get bedrock outcrop, it seems almost random. And that's why we have all of these paha and inliers, is because the orientation of these and placement of them is random. It's not completely uniform. So we get these outliers, these regions where bedrock is, and then that protects the landscape downwind from sand. And the orientation and width of these channels matters quite a bit, because if you have a valley that's oriented with the wind, it can then act as a fetch, so where it can gain strength. But if you have the same channel and it turns against the wind, well, then you're going to have a topographic barrier. And we have to think about sand as the tool. So where can sand get out? Where can sand stay in place? So sand gets out where the channel is not steep and aligns with the wind. And boy, if we just look at the landscape, it really shows there's something going on with the northwest direction. Look at the orientation of all of these features. It really is key, because it cuts across all of these watersheds. So what is forming this can't be fluvial, it can't be an ice burst event, because that water would still follow the topography. This pattern cuts across watersheds, rivers, streams. It's due to the wind. So part of this, to explain the problem with all of this, or to really illustrate how sand is in control, I mapped all the dunes in eastern Iowa, and now Iowa, because I got bored. And from that, I got vectors, or wind direction, from the parabolic dunes. And these dunes are occurring when the Des Moines lobe is coming into place. So keep in mind, though, dunes form when the landscape starts to stabilize, when you get vegetation, or the source shuts off. But in this case, the climate's warming up. You're not going to have as much erosion from paraglacial stuff, but you're still going to have sand deflation until the dunes stabilize. So these dunes are young relative to the rest of the landscape, and there was also sand just blowing across it before the dunes had time to stabilize. And here's an example. This is from the Chia Fen in Johnson County. And the Chia Fen is forming giant sand dunes, and you can see the shape of them just clear as can be. And these things are massive. They're 30, 40 feet of fine sand. And that lends the Chia Fen its unique vegetation, because it's so nutrient poor, because it's formed in quartz. There's no nutrients for these plants to have. And they're sitting high in the landscape, so you can't get water coming in to refresh that area. So from this, I looked at, or used some trigonometry and measured the orientation of those fetch directions, and came up with about 300 degrees off of north. and it's pretty tight. That is a very tight distribution. So it's indicative that there is one direction and it's super strong. That's the dominant force. It's from the northwest. This leads us to these linear features that I touched on earlier. So these aren't formed from in sand, they're formed from sand. And that's, once again, the key. Sand is the tool. And where sand can go, you're going to have changes. And so I mapped out paha ridges. I mapped out slope breaks, so where there's less and where there's not, that contact. I mapped out these troughs and then what I'm calling deflation zones. So where are they? Or what are they? These troughs, well, what they look like, these are actually on the southern Iowa drift plain. So this is off of the erosion surface, but you're still getting the same process, but in a different form happening because it's a different orientation of the landscape. And so these are where streams, like first order streams, line up with the wind and allow the wind and whatever small amounts of sand is there from the alluvium to basically cut them back. And you can see how they all align in the same direction. And the thing is that these are formed in loess, not till, because till is impossible to move with the wind, but wind-blown dust sure is. The other thing that I'm mapped out was these linear ridges. So they're not true paha because they lack loess, but they have the same orientation. And so what I'm now realizing after seeing derecho sightings is if you have trees and these hills and you have a really strong windstorm, well, you're going to actually have more tree throws on the side of the hill than the top. And what that's going to slightly do over time, especially if you have one wind direction, is bevel out these landscapes by churning up the soils on the sides but not the tops. Maybe. This is a work in progress. And so this is right adjacent to the Iowa River, and then 1 mile south you can see there's no orientation in any of this. It's not affected dramatically by deflation and the Eolian patterns. So the last thing, the thing that is most stark, I would say, is these slope breaks. And what I mean by slope break, well, it's where you have a flat area and it's that zone where the inflection changes and you get steep topography. And guess what? They're very linear, but they stop where you have existing drainages. So you have these flat zones, these straight zones, and that's where sand can go and deflate. So I can say that because guess what? The linear feature orientation matches almost 1-to-1 with the sand. And so that pattern is super strong. The correlation is great and the causality, I am pretty sure about that. So how do I prove that it's causing it? Well, what we can do is look at where do we find these patterns and how they match up with the orientation of the rivers and the sand dunes. Because this topography isn't new, it existed, it was just slightly modified during the formation of the Iowan surface. And the width of the valleys would provide a good indication of where sand can and can't get out and where the location of bedrock is too. So this is in Benton County where I've been mapping recently. So what I did was I created a grid of stripes across all of eastern Iowa and then calculated how wide the stream valley would be in that orientation. So it's kind of like this. So zones where you have a lot of length can act as fetches where wind can pick up strength and speed and sand, and then if there's not bedrock on the outside of them, that's where you're going to get sand coming out and forming dunes. And guess what? This is what it looks like. So the deeper the red, the more fetchability it has, the wider it is oriented to the northwest. And that's where you get all of the sand dunes. They come off where you have wide, flat valleys. But what you don't get are dunes coming off of rivers that didn't catch outwash, like the Wapsipinicon. But eventually, the cedar provides so much sand that it flows over into the Wapsi, and then you start getting dunes off of it because this area in here has bedrock, and it catches the sand and then funnels it down. And so now it's in the alluvium, and then it becomes part of that system, and you can blow it out later in the floodplain. Local sources of sand also exist, but don't form dunes. So due to all of this periglacial erosion, you're going to have sands and gravels in these valleys. And that's why this is the same paha we looked at earlier to disprove Rui's model. Well, guess what? There's a little pinch right here where sand is going to fall in. So you get a paha here, but then it widens out. So you're not going to get any loess deposition here. But these channels will catch sand and divert them. But Hinkle Creek right here, this is super wide and full of sand and gravel, which would have provided a sand source to deflate downwind. So it's all about where sand can travel and where you can pick it up again. And so these slope breaks are caused by sand deflation. And they form basically the Iowan erosion surface boundary because of wind. So right in here is near Belle Plaine and Blairstown, and you can see there's this ridge that's 40 feet high and goes across the landscape, and you can see it as you're coming across that highway going east-west out of Blairstown, and that's caused because Prairie Creek right here turns, and that's the southernmost extent of this valley, and guess what? It's full of sand and gravel from periglacial erosion. And that would provide a source for sand to blow out and deflate right along here. But this zone, this creek, is super tight, so it would have caught any sand coming from the northwest. And that's why we have this pattern. And these are areas where I've cored, so I know what's going on here geologically. And this line, super straight, caused by sandblasting. And this is one of the transects showing that, hey, it actually is sandblasting, because you have the original topography, the Sangamon, the old surface, it comes up and then is cut by sand. So the loess would actually protect it from periglacial erosion because it can't hold water like that clay-rich till can. And then when the sand comes in, this then would have been exposed to A, the sandblasting it, and B, the cold temperatures, which would have cause it to fall apart and flow into Prairie Creek. And this is what it looks like. These are the cores that I showed earlier. So here's the loess, here's the Sangamon soil, really old, and this is just proof that the loess acted as a buffer. So pajas, well, they formed during the last glacial advance because of where they sat on the landscape relative to bedrock and steeply incised valleys. And that's why they have their distinctive linear shape, because they're formed where you can deposit loess and not have it be sandblasted. But to the sides where sand can get out, yep, that's where you're not going to have this dust accumulating because it's being deflated. So here's an example. We have bedrock, 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 but it's not wide enough, and you can get some creep up here, but right here it's super steep, and so you get pajas. And then these pajas exacerbate because it causes turbulence, and then the sand can't get picked up in here, but you'll string them out, and that's why they form congeries, not because they group, but because they cause turbulence in the wind. So pajas are not relic surfaces, they're accumulations. So yes, they are old surfaces, but it's not because the loess wasn't there originally. The loess acted as a buffer to protect that, and that's why you have certain areas the loess wasn't getting to, and you lose the Sangamon, because that periglacial erosion was happening before and during loess deposition as well. And these inliers are just massive accumulations of loess due to bedrock cutting down. And this is, again, from Benton County. This is the Cedar River, Vinton's right here. And these two shapes, these inliers, have 50 to 60 feet of silt accumulated because they're right next to the source, the Cedar River. But there's bedrock right here. However, there's not bedrock in here. And I know that because I mapped it, I did the bedrock topography, and there's an old channel that was buried by the most recent glaciation or successive ones that cuts down 100 feet, so the bedrock drops away, and that allows for sand to be funneled through here and just sandblast this all to pieces. But if you the sand try to get into these inliers here, it would bounce off. And so that model works with the assessment from the orientation of the rivers as well. So you get sand dunes pouring off where there's a lot of fetchability, but because there's bedrock here, regardless of how much the sand can pick up, you get protection from that steep surface. So the key point is the Iowan surface at any point is due to there either being a fetch upwind or barrier upwind. If you have a fetch, you're going to have deflation, you're going to have sand, but if you have a topographic barrier, you're going to be able to accumulate loess because of the lack of sand. And the size of that really is the key to understanding these different features. So the largest, though, is the Iowan erosion surface itself, where there's net deflation, but the largest topographic barrier actually is the Southern Iowa drift plain, because the Iowa River is oriented with that northwest wind. So it carried all of the sand away from this area, protecting it from being sandblasted, because none of these streams within the Iowa or the Southern Iowa drift plain in this zone could carried outwash because it didn't connect with the Des Moines lobe. And this is where the balance is. So this is on the erosion surface where there's net deposition or net erosion, but you get these big piles of loess. But on the Southern Iowa drift plain, where you have the Iowa River finally turning just a little bit, you have this big, what I'm calling a deflation lobe, where North Liberty is, because all of the sand finally was able to get out and just sandblast through this area, leaving a smooth, flat topography. But less can pile up, so you have the slope. On the small scale, you have pajas, where you have bedrock in steep rivers. And then on the Southern Iowa drift plain, you have these troughs. So it's a yin and yang. And that's where this comes into play. So it just depends on if it's a fetch or topo barrier, if it's short or if it's wide. And that's why on an area that's net erosion, you're going to get areas of accumulation. On areas of net accumulation, you're going to get areas of erosion. So that's the story. The Iowan surface was originally glaciated, then there was periglacial erosion. Then it was affected by strong winds and sand from outwashing from the Des Moines lobe. The Cedar River, since it twists around, because it was the actual river of that older lobe, is able to pour out sand, but the Iowa River largely matches up with the northwest wind direction as a pure coincidence, and thus funneled sand down, protecting the Southern Iowa drift plain from mass deflation like what was on the Iowan surface. So this is it. This is the model right here. But this is the moral of the story. Net loss of material on the uplands of the Iowan surface, net gain where there's less accumulation, and in the valleys due to periglacial erosion. So this is the real relationship of all of this. It's pretty convoluted, but in order to understand any part of it, you have to be able to follow what's going on in any other aspect of it. So this is just showing that this is how things are occurring over time. It's a pretty complicated figure, but you know, I won't talk about that too much. So that's it. That's the conclusions. If you look at patterns and catalog them and put them together, you can figure stuff out. Time of the erosion surface, once again, 500,000-year-old glacier set up the orientation. There's another glacier that affected the northern part. Then the LGM got really cold and it outwashed in silt, and then the wind affected the rest of it. So that's it. The wind giveth and the wind taketh. So I will now take questions if we have any. Here we go. I have one from Gene. How long would these winds have had to be blowing in order to get the more or less same direction to get these paha? That's a good question. So what we're seeing, we can date the base of these paha because there's a soil there that has organic material in it. And it shows that the lust started to accumulate about 26,000 years ago. And then that lust shuts off at 13,000 years ago. So the wind was probably blowing in the same direction during that time period because that's when the ice sheet was really hanging up over this part of the Midwest. So there were time periods, though, in that were more extreme due to climate being drier or wind being more gusty. And I think that period was 23 to 20,000 years ago. Okay.
Absolutely fascinating, Phil. If folks have questions, please get them typed in here. I'm blown away. Now here's a question: did I miss why the Wapsipinicon is different?
That Wapsi. So the Wapsi is different than the cedar, even though it has the same rough orientation, because it didn't collect outwash from the Des Moines lobe. Whereas the Iowa and the cedar were beheaded, is the term for it. They lost their headwaters, and then they were just pumped full of meltwater as that Des Moines lobe melted. Whereas the Wapsi didn't. So it sits just a little bit further to the east, and so you didn't get that outwash which filled the valley and then allowed water or sand to blow out. But you still got Aeolian sand coming across the landscape from the cedar, and so that's why it's a transport surface, because you can just move sand across it. And it's not super obvious because that sand on the Iowan erosion surface, if you dig down, is only a couple inches thick. But then it's also worked in with loess, so people have called it loamy sediments, but it's not. It's Aeolian sand and Aeolian silt then worked together, and then you have maybe like half a yard of silt on top of that, and so that's where you get your decent productive soils.
Just getting that typed in here. Excellent.
All right, did I miss any other questions?
Not so far here. We'll see if anyone else has any final ones. Again, just a reminder, folks, this is being recorded, so we'll have this up here in a couple of days. There's definitely a couple of slides I want to go back and check out. Phil, that was absolutely fascinating. I love just how the interactions play together, whether it's the forming of the river, whether it's the outwash from the Des Moines. I mean, all of these variables come together in this very unique way. And I was reminded as I'm listening to your presentation of like a Sherlock Holmes episode. It was fantastic because we finally get to the end where you bring it all together.
Yeah, and that's why this area, I mean, honestly, there's been people who have these different interpretations, but what they can't do that I can is have computers. None of these people who have been previously looking at this, I mean, I can zoom in and see people's houses and all of North America with like 3 scrolls of my mouse wheel. And so I can look at these patterns on a local and continental scale. And so that's the big difference. But in order to understand any problem, especially this one, because there's just so much, you have to put all of the data together. And that's something that is difficult unless you have a way to do that. And that's why GIS is really great, because I have a layer for all the different soils, for where bedrock outcrops. I have all of the rivers plotted at once. And then I have my dune maps and my loess maps and my drill cores, and all of this is just in one place. So in order to look at it, you can just look at it, take one part out, rotate it, and you can even put it in 3D too. And so that's computers are great. And that's why in the title, I call myself a little computer nerd boy.
Here's another follow-up question from Jean Marie. Do you have any sort of visual timeline of each of these processes?
Not really, because in order to get a timeline of something, you have to understand rates of accumulation and deposition. And I haven't been able to get samples that I could analyze for that. And those are also, that takes money. So in order to get at rates, I'd have to collect different sand units in the dark and then process them for optically stimulated luminescence dating to see the last time they were exposed to the sun, and then that different time period over time. But that wouldn't reflect the erosion and only show when that sand dune formed. And so that's the key point to any of this analytical techniques is what are you actually doing? What are you recording? What are you showing?
Gotcha.
So yeah, this is why it's just like kind of static models, and I don't know how to animate very well. So
hey, a quick follow-up from Steve. He wants to know, is there a map available showing all of the Pajas that have been identified?
oh yeah, the Iowa DNR has, I think, the Iowa Geoportal, and I think all of those are in shapefile, but I think there's shapefile to KMZ converters out there. So just Google Iowa Geodatabase, and I think in geology, glacial geology, or landforms, it should be in there, because I use one that's been generated, but I've modified it to my own needs.
Well, and Steve put behind that question KMZ, so he must know exactly what you're talking about with some sort of file type or something there. So
yeah, shape files are for ArcGIS, and KMZs are for like Google Maps.
Cool, cool. So Wendy has a curious question here. Is any of your research available for anywhere in Floyd and Mitchell counties? What's going on up there?
We have maps available on our website, iowageologicalsurvey.org, in the publication section. If you also Google Floyd County geology maps, it should come up as well. And so what's going on in Floyd and Mitchell counties, it is different because of that recent advance. And so Mitchell County is almost completely covered by that advance until about the Little Cedar. And then in Floyd, it seems to cut down to the Cedar and then over to the Shell Rock. And so that's why as you go towards Osage, it just gets super flat. But as you go east towards Riceville, the topography starts to pick up, and that's because it wasn't as recently glaciated.
Fascinating. Hey, Greg asks, does the rate of glacial melt affect how these interactions occur?
I would say probably not. It has to do more so with orientation of the landscape and the climate. So if it's really dry, if it's really windy, that matters more than if there's 100,000 cubic meters of sand and gravel versus 50,000 cubic meters. Because if you can't blow the loess and silt out, it doesn't matter how much there is. So it's just like an order of control thing. But you have to have that material there to be blown out too. So, you know, there's multiple levers.
All those variables. Yeah. Well, I think we've got most of these. Oh, one quick one here. How much of your training involved computers?
So I use, I'm a millennial. I use a computer every day, and I grew up with one in my house, starting from when I was 12. So I'm self-taught on a lot of things, but there are classes and there's online courses too that I've watched. YouTube's great for certain things, but once you start getting out of basics, then you're just like searching through like Stack forums and saying, why is my shapefile not linking? Oh, it's because my my data is in letters and not numbers, and so it's just yeah. Self-taught. Just if you want advice, don't get frustrated with computers. Find them interesting and not a burden. I wish I could say the same thing about cars. I just hate fixing them. And it's too big. They get hot and bloodied.
Well, we've gone a little bit over here today, but I want to thank folks for sticking around. Phil, really want to thank you for hosting here and giving us some insight. Again, I find this just absolutely fascinating. We're going to have you back sometime. What's the next project you're working on that you can share with us down the road?
I'm getting a PhD, so I can probably talk about that. But it's more on how that shape of the Des Moines lobe. So what I presented on how lobes affect drainage patterns, that's my first part of my PhD. So I have that like roughed out. And then from that, why ice comes into Iowa from the north, because Iowa has been completely glaciated. There's no part of Iowa that has not been covered by ice. So people up there who call Decorah the driftless region, They're wrong. But Wisconsin has been truly unglaciated. So parts of that in the Wisconsin driftless, ice hasn't touched that. And why is that? Well, it has to do with all these different factors that deal with the rise of the Rockies and, you know, old paleo seaways and stuff like that. So
another Sherlock Holmes episode, certainly. Let me know when that time comes, and we'll be sure to get it scheduled. So,
all right. Well, thank you for listening. I hope most people got something out of this.
Have a great day, everyone. Thanks so much, Phil. Take care now. Bye, folks.
Thank you.